Okay, so welcome to the last video for the week, where we're going to discuss the derivative of the logarithm, the natural logarithm, so derivative of ln x. And Puccini's coming to join us for this last video. You want to be here for the first one and the last one, huh? Okay, you just woke up? All right. So I'm going to tell you what the formula for the derivative of ln x is. It's not hard to prove using the chain rule. It requires a little bit more sophisticated version of the chain rule that we didn't do, but it's not like a quantum leap. So using a slightly more general version of the chain rule. This up a bit. Pen is acting a little weird. Sorry about that. One can show the following. That the derivative of the natural logarithm function is 1 over x, so long as x is strictly greater than 0. Okay, so that's just something you'll have to kind of memorize for now. It's not a hard formula, fortunately. So as we did with the with the formula for the derivative of e to the x, we can combine this with the chain rule to be able to compute some pretty derivatives of some more complicated logarithmic functions. Luckily, we will not have to do the second derivatives of these functions. As I was saying at the end of the last video, the second derivatives get very, very hard, but you'll see why in the examples, but we won't need to do that. Okay, Kat, you need to find a place to settle down. Okay, so we can combine this with the chain rule, this formula, with our knowledge of the chain rule. To compute the derivative of functions of the form ln composed with g of x. Okay, so ln and g of x. So in this case, okay, we want to compute the derivative of ln of g of x. Well, you recognize, I'll write this in gray, but you recognize that ln of g at x is f composed with g at x, where f at x is ln x and g at x is g at x. Okay, so then, right, according to the chain rule, the derivative of ln evaluated at g at x is the derivative of the outer at the inner function g at x times the derivative of g at x. And of course, from what we said above, the derivative of ln we have above is just 1 over x. So this is 1 over x. And so what you get is 1 over g of x times whatever the derivative of g happens to be. So the derivative evaluated, right, at g at x is 1 over g at x. So I'll finish this formula here. So that's the proof of the formula using the chain rule, the version of the chain rule we know. So it's g prime at x over g at x. So it's a very straightforward result. Oops, sorry. He's found a toy. I don't know if you hear him mess around with a toy in the background, but we'll let him be. He's occupied, which is good for us. All right, so let's do the rest of this section is just to kind of, so that's the only new thing in this section, this derivative of ln x, and then combine that with the chain rule to get the formula in the box, this red box here. And the rest of the section is just working out examples. So we'll deal with that. Okay, so examples. So in all these, just differentiate the following functions. So the first one is actually quite easy. It's just 12 ln x. The one I'm going to give you is 12 ln x minus 3 e to the x plus ln of 4 minus e to the 5th. Okay, so y prime then, okay, is the derivative of this guy. So I'm going to write it like this. So it's the derivative of 12 ln x minus 3 e to the x plus the derivative of ln 4 minus e to the 5th. Now, this can throw people a lot. I want you to look at this carefully, right? This, even though it looks ugly, is just a number. E to the 5th, whatever that is some kind of number. ln 4 is a number, right? So the derivative of this is the derivative of a constant. So this is just 0. Now here we have to do some work, but it's not hard. Oh, let me change back to black ink. So y prime, using our derivative rules from the beginning of the semester, is 12 times the derivative of ln x minus 3 times the derivative of e to the x. And now the derivative of ln x is, we just said, is our new formula 1 over x. So this is 12 times 1 over x. And of course, the derivative of e to the x is just our friend e to the x again. So what we get in the end is something quite straightforward. It's 12 over x minus 3 e to the x. Okay, so this I didn't even need, so this was just using the derivative of ln. I didn't need to use the, this other formula with the chain rule